And I must say I've really enjoyed this meeting very much. I'm sorry that Jorg isn't here to thank him, because I won't be here tomorrow because of KLM changing my flight. And it's been a great pleasure to talk to so many young people. I was sorry to have to disillusion one person last night by saying that you don't get oysters at every conference. It was his first conference and he thought that was standard. Anyway, I'm sorry for this rather forbidding title, but I'm going to talk about something that I think is quite important. The motivation is an attempt to understand the differences between the energy spectra reported by the Auger and TA observatories. And I want to stress that the differences, as we saw in Dr. Fujita's talk this morning, the differences are also seen in the common declination band that is visible to both instruments. And until we really understand and can get those two fluxes to agree, any suggestions that we see north-south differences, I think, are not going to be believable. Now, the important thing to note at this stage is that the events that the TA group use, which are on a square grid, use an LDF from Agasa. That, I think, itself is an unfortunate thing, because the climate at the Agasa site is totally different from the climate at the TA site, and that's well understood and well described by Lindsley about 40 years ago. And what I'm hoping to establish is that the misestimation of the estimator of the shower size does have an impact on the spectrum. Now, this talk is going to be a little bit technical, so I'm going to start with some historical background. Now, the question is, what do you measure to get a good estimate of the energy? In the beginning, when looking at showers produced by primaries of 10 to the 15 or 10 to the 16 electron volts, typically one was using Geiger counters, and you were able to measure the total number of electrons in the shower. And that can be related through the model calculations of the time, the analytical calculations of Nishimura and Kamata in particular, to the primary energy. Now, sorry, I hate these things. Now notice that if you plot rho, the density, against R squared, for a scintillator array, you get a very different distribution of the number of particles depending on the lateral distribution function. And here you see the median, and that is less than a Mollier unit. If you were able to measure Cherenkov light or to measure muons, then things are much more favorable, because the distance at which you get the median number of particles or the median amount of light is much further out. Now, I want to emphasize two important things at this point. Firstly, measurements that were made at Volcano Ranch with scintillators and with water Cherenkov detectors at Havre Park, both ancient experiments, both closed down in the 70s, no, the 80s rather. They enabled us to see shower-to-shower differences in the lateral distribution functions. These are not measurable in the giant arrays that we have at the moment, because we can't afford to put the detectors close enough together. The other point I want to stress at this stage is that at 10 to the 17 electron volts, the RMS spread in N for a given energy at ground level is about 70%, while at 950 meters from the axis in a water Cherenkov detector, it's only 6%. Now, those of you who don't work in this field might find it rather surprising that you do much better by measuring a signal at a vast distance when most of the signal is inside. And that's really because of the fluctuations that take place in the development of the shower. Now, as rays became larger and larger, the detector spacing had to be increased just because of cost. And they soon became to increase till there were more than several Mollier units apart. So that we go back to this picture here, you're actually going to be working with detectors which are in this region. So you're not going to see most of the signal. Now, in the early days at Havre Park, we recognized this, and we tried to counter it by measuring essentially the energy flow, the energy that was deposited between 100 meters and a kilometer in our water Cherenkov detectors. And that's actually about 150th of the primary energy. But the problem is that the variations of this power law here with energy varies from shower to shower and also with energy, and that was a big problem. And generally, as I said, on a close-packed array, you can measure the LDF, but on the wide spacings that you have on the giant arrays, you cannot. You have to have something that's really compact. Now, Michael Hillis, whose name has been mentioned many times at this meeting, was a remarkable man and made huge numbers of contributions to our field. He was never a member of the Haver Park collaboration, but he did get hold of 50 of our early events, and which were taken from the star-shaped geometry that we had at the time. This was an engineering array. Each of these detectors was 500 meters apart and was 34 square meters in area, so they're large area detectors. And they formed the nucleus of the hexagonal array of 12 square kilometers that we eventually built. Now, what Michael found was that if you fitted the data from these events, no Monte Carlo simulations, with lateral distribution power laws, which were reasonably in accord with the data, then at 500 meters, the spread was something like 12%. Whereas if this parameter E100 was used, it was more like 70%. So this gave us something that we could measure without knowing the lateral distribution to a high precision. And these were for showers of perhaps a few times 10 to the 17 electron volts, so smaller than the showers I'll be talking about later. Now, at Haver Park, this surrogate for the energy of which we called Rho 500 was adopted for the engineering array. And then when we completed the larger array, we essentially made an educated guess and went for Rho 600, and that turned out to be pretty good. Now, we weren't able to do simulations because at this time, the computer that we used weighed 4.7 tons, cost many millions of pounds in 1960 pounds, not in today's pounds, and had 122 kbytes of memory. So the fact that Hillis was able to do anything was remarkable. It took something like 4 minutes to analyze an event from 4 detectors. So don't be too critical of us not following this up. Now, when we came to work at the OSI Observatory, we hadn't done actually in the design study the requisite simulations. And Jim Cronin and I guessed that 1,000 meters would be a good distance to choose for the what we now call R-opt. And a detailed study was done largely by David Newton, one of my research students, looking at this in detail. And here you see R-opt for different lateral distributions, a power law, the Haver Park lateral distribution function, and an NKG type. I won't bother with these details. And the differences between the values that you see here are typically much smaller than the spread that you get, show a spread smaller than you get at a kilometer by about 2%. So that should say 1,000. Using 1,000 meters rather than a smaller value is not very important. And in any big collaboration, as you will know, there's incredible inertia. And the idea of moving from 1,000 meters to say 950 meters didn't seem reasonable. And also it would be something that we'd have to explain at every meeting. Now, in that work, what we showed was that the signal round about a kilometer was varying very slowly with second theta and hardly varying at all with energy. If one of the stations was saturated, and this happens because of limitations in the electronics, which are again set by cost, then again, you got a larger value of R-opt, but the change with energy and with zenith angle is relatively small. So the result of the work that we did was to explore the dependence of R-opt and the detector spacing, establish that for a triangular geometry, or I sometimes call it hexagonal geometry, 2/3 of the spacing is an appropriate choice for R-opts. In the case of Auger, which is a 1,500 meter spacing, S1000 seems a pretty good choice to make. And that certainly works for the 750 meter array of the Auger Observatory. It's been used and it's been checked. And it's used, but not checked, by the telescope array for a square array. Now, if you remember, we just go back a couple of slides, this pretty awful geometry on the engineering array at Haver Park, 500 meters was the value and 500 meters was the spacing. So it occurred to us that it was really possible that the geometry, the layout of the detectors, had fact had an influence on what our op was. And this is a very early, very crude result where simulations were made for the telescope array with Water-Cherenkov detectors for 2 energies in a range of angles. This is the 800 meters that's used by the telescope array, and you see it shifts. It should actually be something like 1250 meters, but it changes with energy, quite different to what you saw in the analysis for Auger. And here you see for vertical showers for protons from a simulation, the blue is the lower energies, the red is the higher energies. You see that there's very little dependence on energy, and the uncertainty gets smaller as you go to higher energy. Here, of course, the uncertainty is nice and small at R opt, but at 800 meters, it is larger. So that is something to worry about. This is just a more detailed comparison of the results from a triangular and square grid. The triangular grid is on the left, Auger with the NKG function. The square grid of a Gasa is shown here, and you see as you go up in energy, there's a shift in the value of R opt and a corresponding worsening in the accuracy with which you can make the measurement. Now, that's part of the story, and it actually turns out not to be the biggest problem. The biggest problem is to do with the lateral distribution, and there are fluctuations in the lateral distribution because of the way in which the shower develops. There aren't 2 showers the same, essentially. And it turns out that these fluctuations are asymmetric. And again, in the case of the triangular grid, there is practically no variation in there's no bias in the measurement that you make as a function of energy for different angles. This is not 32 and 48 degrees. Whereas in the case of the square grid, the situation is quite different. The bias can be quite large as 20% at the highest energies. And this is because of the lateral distribution. Now, have I gone the wrong way? So summarizing these 2 things together, this is putting together the resolution, the accuracy with which you can make the measurement, and the bias. And you see for the square grid, the resolution is something like that, whereas for the triangular grid, it becomes flat at about 7% at high energies, and the bias also goes in a different way. Now, we've heard, sorry, I always get these things wrong. Now, we've heard a lot about unfolding in this meeting. That's what everyone does in spectra. Here, we're actually folding in these biases and resolutions to see what happens. And what we've taken as essentially as the true spectrum is the orange here. And notice if you put the square grid folding, just putting in the resolution, it makes very little difference. At the highest energies, there's a small difference. You can see that the orange line is above the sort of black, the true spectrum. But if you put in the bias because of the lateral distribution, the situation is quite different. And in this picture on the right, points from the Agasa, the TA experiment have been added along with points from the Auger measurement. And you see the situation is very suggestive of what I showed in the first slide. Now, there's a lot of work to do in this still. I'm just pointing out because of the way people are with developing instruments, that there are some take-home messages that are important. The layout of an array has to be considered, and there is a strong difference between triangular and square grids. The R-op dependence should be investigated for whatever geometry you're planning, and it's desirable to have an R-op that doesn't depend on energy or zenith angle. And as I've put in red here, it's a possible contribution to the TA and Auger spectral differences, and active discussions are underway between TA and Auger through the working group in the spectrum. The thing that I find two things I find very frustrating. I do not know why triangular grids were chosen, but if you look back in history, all grids were triangular except a Cascada, where Johannes Knapp told me this was a German wish for precision. Jim Cronin, who had when CASA had a square grid, and we nearly had a square grid if there would have been Auger North, but we didn't. And I'm sure this is a complicated problem. I suspect the lateral distribution is at the heart of it because you get different results from models for proton and ion. Thank you.